Hello everybody and welcome back to another Python tutorial. So in this video, what we're going to be doing is learning about the astar pathfinding algorithm and then actually implementing that into a visualization tool. So this is a really cool video because this project is just really fun, in my opinion, to actually see how a computer kind of goes down the process of finding the shortest path between 2 points. And a visualization tool like this, although it is kind of simple, this isn't going to be a super complicated program, looks really great on a resume and is a really great thing you can point someone to and say, hey, not only do I know how to use algorithms, but I also can implement them into this cool visualization tool, and you can now watch these, this computer figure out the shortest path between 2 points. So anyways, this has really fascinated me. Let me give you guys a quick demo of what it is we're going to be creating, and then I'll talk more about how this tutorial series is going to look, or how this tutorial is going to look, and kind of what you can expect from it. So you can see here, this is the basics. We have just the visualization of finding the shortest path. Now, since astar is actually an informed search algorithm, which we'll talk more about later, this means we can avoid doing a ton of unnecessary searches that we don't need to do. So for example, in an uninformed search algorithm, they may potentially consider some of the nodes over here where I'm kind of drawing and erasing these barriers. And the reason they might do that is because it's just somewhat of a brute force approach. They're just checking every single possible path. They're not actually moving in a direction that kind of makes sense. Whereas this algorithm here, you can see, was always kind of moving in the right direction. It might have gone off a little bit. Maybe it goes down some roads that aren't necessarily correct, but it always is moving in the correct direction, and that is kind of what's guiding the algorithm and making it much more efficient. Now, of course, these gains are way bigger when you have a huge map and a much larger network of nodes connected together. But in this case, on a 50 by 50 grid, which I have, it happens pretty much instantly. And if I omitted actually doing the drawing aspect where we draw the green and red squares, then this would happen pretty well instantaneously. So with that being said, I will quickly say that this is not a beginner tutorial series. Although it's not going to be super complicated, we are going to be using some data structures and algorithms. We're going to be talking about this algorithm, which is not trivial by any means. And well, if you don't have any experience with Python, this might be a little bit overwhelming. So I just want to warn you right now. So with that being said, let's go ahead and start talking about the astar pathfinding algorithm after a quick word from our sponsor. I need to thank Simplilearn for sponsoring this video and introduce you all to their Data Scientist Master Program that was co-developed with IBM. This program is comprised of 6 unique courses that implement a unique, blended learning experience in a high-engagement online classroom environment. During this program, you will master 30+ in-demand skills and work with tools and languages like R, SAS, Python, Tableau, Hadoop, and Spark. You'll master these skills through 15 real-life projects and 1 capstone project during this 12-month comprehensive course. You'll also be given $1,200 USD worth of IBM Cloud credits to use during your 24/7 access to the IBM Watson platform. After completion of this course, you'll be given certificates from IBM and Simplilearn to testify to your skills as an expert in data science. Get started by hitting the link in the description. Alright, so now it's time to understand the astar pathfinding algorithm. So before I go into all the kind of explanations and definitions, I'm going to quickly define what a few terms mean. So when I say node, I'm talking about a letter. Okay, I'm talking about A, B, C, D. This is a node. A node is anything in a graph that you can visit. You can think of it as a vertex, right? Say we have a triangle, you can think of the nodes of a triangle, if you're treating this as a graph, as the 3 vertexes, and the edges are going to be all the lines that connect those. So we have nodes and we have edges. Just understand, edges connect nodes. Nodes are usually represented as a circle or something that you could visit. If we look at a grid, for example, and we have like a 2x2 grid, then really you can draw this grid in kind of a graph format like this, where all of these are the nodes, and then the edges are the connections between these nodes, which could just mean, what it means to like go from that node to this node. That's all I'm saying. Just hopefully that makes sense. And last thing here to explain is when we have an edge, we can have an edge that is a weighted edge or an unweighted edge. If it's a weighted edge, what that means is that it takes a certain amount, or it is a certain length. So obviously weight 1 is a shorter edge than weight 2. So obviously this is not drawn to scale if you're talking about the weights of these edges, but I've drawn them just with different weights so that for this algorithm, it makes sense and we can actually do something that's meaningful. But in our example where we do the astar pathfinding and we're using the grid, none of the edges are going to be weighted. They're all just going to be known as like 1. We'll just give them all weight 1 because we'll just assume they're all the same distance essentially. Okay, hopefully that makes sense. Now let's get into the algorithm. So how does this work? What is the astar pathfinding algorithm? Well, the goal of this algorithm is to find the shortest path from point A to point B in a graph using the edges that are in that graph, right? And anything can kind of be represented as a graph, just like we've been drawing over here and I've been showing you. So how do we do that? Well, this is an informed search algorithm, which means we don't only just brute force and attempt every single path, we actually have what's known as a heuristic function that helps guide us and figure out the correct path to go down. Essentially, as you'll see as we go through this algorithm, we only consider paths that we know are optimal. We don't consider things that have a huge distance to get to them already or that look like they're going to be really far apart. We may consider those, but that's least priority, and hopefully we don't even have to. We end up finding a shortest path before we even consider those nodes. So that's kind of the point of this algorithm, as you're going to see. But I think the best way to explain this to you is really just to go through an example and just kind of slowly go through it as we go. So what we need to do to start is we need to take our start node, which in this case is going to be A, and we need to put this inside of our open set. So we have this open set. This is going to be represented by a priority queue when we actually do this implementation. Don't worry if you don't know what that is. We'll talk about it later. And essentially the open set keeps track of the nodes that we want to look at next. You can think of it almost just as a queue. It's the next things that we want to consider. So we always start by putting our start node in the open set. And we put it in the open set along with the distance to that node, which we're going to say is our F score. Now, I need to define what this F, G, and H score stand for because these are going to be very important as we go through this algorithm. So let's do that quickly. So H score, which is just simply a function, Hn, so H of n gives us an estimate of the distance from node n to the end node. Essentially, we just pass it a node and it looks at the end node and says, okay, I don't really know how far away you are, but like if we're just doing absolute distance, so literally from the center of say A to D, even if an edge doesn't exist here, I'm going to assume you're, X blocks away just based on that absolute distance. That's what this function does. There's many different distance formulas you can use in here. I think Euclidean distance is popular. Some people use Manhattan distance. That's what we're going to use here. Lots of different distances. Anyways, this is just some function that gives us the distance from node N to the end node. There we go. And again, this is not like a super correct distance. This is just a guess at what that distance is based on some formula that we've implemented in there. Awesome. That's the H score. Your G score is the current shortest distance to get from the start node to this node. So if we're talking about the G score of C, then whatever the shortest distance from from point A, which is our start node, to point C that we've currently taken, that we've currently found, will be this G score. And the F score is simply the addition of the G score and the H score. So if you understand that, and I wrote the kind of formula down here so we can remember what makes everything up, the F score is pretty much trying to give us an estimate, say, okay, we've already taken 2 blocks to get to this node, and from this node, we think it's going to take like 5 blocks to get to the end node, so we have a total score of 7. Okay, should we start looking at this one first, or should we consider this next node that has a lower F score, right? Because maybe a lower F score means that this is actually closer and we should take that node over the other node. That's the way that we prioritize which nodes we consider, is by using the F score, and the F score is made up of the G score and the H score. So again, G score is the exact distance, the shortest distance that we found currently to get from the start node to whatever node we're talking about. And if we're talking about node D, whatever the distance is, whatever shortest path we've currently found to node D, that's the distance we're going to have for our G score. The H score is the heuristic, which is just the guess at how far away we are from the end. And the F score is the addition of those two scores to give us an estimate of how far away this node is from the end node, or like what that finalized path would look like. So that is these scores, and they're going to be very important as we go through here. So let's actually start this. We have open set, we have 0A. So of course A is G score, F score, and H score is going to be 0 because, well, it's itself, right? At our start node, we can't have an F, G, and H score that's higher than 0 because we're just already at our same node. Hopefully that makes sense. Now the rest of these scores though, we're going to start them at infinity, and you're going to see why, but just imagine the H score is not really relevant right now for these ones, but just they're all infinity to start. Okay, so we start them off at infinity because currently we have no idea. We have not found any path to these nodes. We haven't considered anything from the start node. So we just assume it takes infinity to get there. That's just our main assumption. And these might actually stay infinity because we may never actually even consider them. So we have 0a, and we pull 0a out of the open set. We've just set everything up. We've, initialized our table. We pull it out. So we delete it from the open set and we start looking at it. So, okay, we're on node A now. We're considering node A. I think I'm just going to underline what node we're currently looking at. So I'll just underline it like that. We're looking at node A. And the first step is to look at the neighbors of node A. So in this case, the only neighbor of node A is C. And there's only two ways to get to node C. There's two edges. So we have the 2 edge and the 1 edge. So we start by just looking at any edge. There's no order we take and looking at it. So we say, okay, to get to node C, we have edge 1, right? So we have this edge here. So what we're going to do is we're going to say, okay, is this edge that we've currently taken, like the current path to node C that we're on, how long is this path? What is the current path? Well, the current path is distance 1. So we compare that now to the G-score of node C. And we say, okay, is the current score that we're looking at, score 1, shorter than the current G-score of node C? So we compare it to infinity, which is right here, and we say, which is shorter? Well, of course, distance 1 is shorter than infinity or smaller than infinity. So we go ahead and we update the G-score and make it 1. And we say, okay, now currently the best path we know, the best we've found to get to node C is from node A to node C, taking edge 1, right? Taking the edge with weight 1. So we update that score. Then we go ahead and we update the H score. So we say, okay, since we're considering this node C now, we found a better path. We're not skipping over it. This is the correct way to go. What is the H score, the tentative distance from node C to node D? What is our guess for that? Well, our guess for that, we can just kind of make that up. I'll just say, oh, we think that's going to take, 1 distance point to get there. So I'll just write 1 here. Of course, obviously it's 2, but we don't know that. We're just taking an absolute distance guess. So we take a guess of 1, and then we update our F score and we say, okay, well, the F score now is going to be 2 because, of course, the G score and the H score added together is 2. And once we update the G score, we update the H score, and then we update the F score accordingly. So hopefully this is all making sense, but this is the basics of it. So 2, 1, 1, those are our scores. And then we go ahead and we update this last, which tells us where we came from to get these scores. So we came from node A to get to node C. There we go. That just tells us what node was the last node we came from. Awesome. Now I'm actually just going to delete this other edge because for our example, we're not going to do anything with multiple edges. So I think it'll just make more sense to do this. So let's go ahead and do that. So now once we've considered this node and we said, okay, this was the shortest path, what we do is we take that node, and I'm just going to erase some of this stuff now to clean it up, and we add it into the open set. So we say, okay, we've considered node A. Now we just looked at node C as a neighbor. So let's throw that into the open set. So we're going to say, okay, what's the F score of node C? That's 2. Let's add that to the open set. So we say 2C, saying the current shortest distance in the open set is 2C. Now we look in the open set and we say, okay, give me the node that has the shortest F score. Well, there's only one thing in the open set, so we have to use this one. So we take it out, and I guess I can just move it like this if I really wanted to. Oops, I forgot a bracket. Let's move that there. So we take this and we move it out of the open set and we start considering node C. So double underline, and now we do the same thing. We look at the neighbors of node C. So let's start by going to node B. Let's look at node B, and we go, okay, so what is the current distance that it takes us to get from node C to node B? Well, we got to go from A to C, that's 1, and then from C to B, that's 4. So our current kind of tentative G score right now is 4. So we say, all right, if we're using node C to get to node B, we're going to have a G score of 4. So we take 4, right, and we compare it to the G score of B. And we say, okay, is that larger or smaller? Well, that is going to be smaller. So we update the G score of B, and then we go ahead and we update the H score and the F score. So what's the H score from node B to node D? Let's just say that that's a distance of, let's give it 2. That's going to be our guess. So we'll say, okay, that's going to be 2. So now our F score is 6. Now we've looked at node B, we've considered the neighbor, so we add node B into the open set with its current F score. So we say 6B, and that's now inside of the open set. So let me just erase this now to clean this stuff up, and then we'll move forward and we'll do the next neighbor. So of course the next neighbor is D, which so happens to be our end node, but don't worry, we're not done the algorithm yet. So we go from C to D, and we say, okay, what is the tentative G score that we've kind of just calculated here between node C and node D from the start node? Well, that's of course going to be 3. So we go here to the G score and we say, okay, well, is that less than infinity? Yes, it is. So we update that. That becomes 3. What do we do next? We update the H score and we update the F score. So let's say that our guess from node D to D, well, that's obviously going to be 0. So we'll put 0 right there. And then what about the F score? Well, that's just going to be 3, right? So there we go. So now we go into the open set and we put inside of here 3D like that. Boom. So now we've considered C. We're done with C. We can erase this right here. And let me just fix this bubble. We can erase this 4. And now we go into our open set and we say, okay, give me the node in here that has the shortest F score or the lowest F score. Well, of course, that's 3D. So we pop 3D out of here. And as soon as we do this, as soon as we take the end node out of the open set, we immediately finish the algorithm. And we know that the shortest path now has to be from A, oops, it was not supposed to be an eraser, from A to C to D. Now, the reason we know that, and let me just actually fill some of these things, and I forgot to fill in the last column. From D, that was C, from B, that was C, and from A, the last would have just been nothing. But anyways, this is what our last column would look like, so the node that we came from. And essentially what we do is say, okay, we found D, we know this must be the shortest path, because if D was in here anywhere else, we would have picked it out and it would have had a shorter F score, right? Because we picked out the smallest F score. So we reached D, we took out the last node, and now the algorithm is complete, it's finished, and all we have to do is find the path. Now, the way we find the path is we just backtrack. We say, okay, D came from C, C came from A, so that must be our path right there. And that is our path, and it so happens to be the shortest path just by following that formula. Now, of course, things can get a little bit more complicated and there's more edge cases and things to consider, but that is the basics of this algorithm. You have this H score and this F score and this G score that help show us where we should be going, what direction we need to move in, and what nodes we consider next. So let's just imagine for a second, though, that maybe we didn't just immediately consider this end node, right? Maybe we didn't hit the end node. Let's just imagine that actually D maybe isn't necessarily the end node. Maybe there's another node here that is the end node, and that's our new end. Then what we would do is we would simply, since D was already in here, we'd pop it out, we'd consider the neighbors of D. So we considered C, we consider B, and we consider E. And remember, if I'm considering B, what I would be thinking about is, okay, so to get from A to C to D to B, what is the distance going to be? And of course, that distance is going to be larger than whatever the current distance was, the current G score to get to B. So actually, 1, 2, 1 is going to be the same. But since it's the same, we don't bother updating it. We just say, okay, we don't need to update that because obviously the current distance to get from A to C to D to B, well, that's 4. The distance that we have as the G score, that's 4. So since that's not smaller, we just don't do anything. We just skip over B and we say, okay, we don't need to look at that anymore. We're not adding it back in the set. We're just moving past it. And then we go and we consider D, or we consider C, and we consider E. So we do E, or C. We determine that, well, to get to C is obviously not shorter to go A, C, D, C than it is to just go A, C. So we don't update that. And then we consider E. We'd update E in here with whatever the values are. We'd add E to the open set. The distance for E would almost likely be larger than the distance for B. We would take out B, we would consider that, and that's how we would keep going. So I know I'm kind of just fast forwarding through the rest of the algorithm. It does take a long time to walk through, but that is the basics. And of course, as we go through this, it's going to start to make a lot more sense, but that is how the F, G, and H score work. And hopefully you understand how we're considering nodes that are closer first with that estimate of that H score, that G score that's telling us the actual distance, and that F score that's the combination in between. So anyways, that is going to be my explanation. If you don't understand that, I'm going to recommend you head to Wikipedia, maybe rewatch this, see if you can do this yourself on your own graph, maybe do it on a piece of pencil and paper. But once you feel comfortable, let's move forward and let's actually start coding this out. Okay, so sorry for that long explanation, but I really do try my best to make sure you guys really can understand everything so that I'm not just blindly going through and showing you that. And even if you don't understand completely, I will be re-explaining as we get to the implementation part. But now let's actually start working on this visualization tool and more of the fun stuff. So the only real prerequisite for this is to install Pygame. So Pygame is a 2D graphics module in Python. Really easy to use. I'll explain all the stuff that we do here. But to install that, go to your command prompt or terminal, and you're going to type pip install Pygame. Now, you might, if you're on Mac, be able to use pip 3. So just try pip install Pygame. If that doesn't work for you, I'll leave a card to a video that explains how to install Pygame, and I'll leave a link in the description as well. If you're on Mac, just replace pip with pip 3, and that should hopefully be able to install it. And then I think you can also try Python -m and then pip install and then Pygame as well. Now these are all just different options you can try, so I'm just giving you a bunch of commands, but in your terminal or in your command prompt, pip install Pygame, pip 3 install Pygame, Python -m pip install Pygame, or Python 3 -m pip install Pygame. If none of those work, or you get like pip is not recognized as an internal external command, watch the video. It should hopefully help you do that. Anyways, once we've done that, I'm going to be working in Sublime Text for this video. You guys can work in whatever editor you want. We're just going to start by doing some imports. So we're just going to import Pygame. I've already made a Python file here. We're going to import math like that. And we're going to say from queue import priority queue. Now we'll be using this later. I'll explain how that works. It's going to be for the algorithm, but you don't need to install this. This should be built into the Python standard library. Now next, I'm going to define the width of my window. So I'm going to make everything square. So I'm not going to have a height. I'm just going to have a width. And I think I'm going to make that 800. So width 800, and then I'm going to say win. And then in this case, that's going to be equal to pygame.display.set_mode. And inside of set of brackets, I'm going to go width. So what this does is just set up. Why is this not working? Width. I'm hitting enter. It's literally canceling what I'm typing. Okay, anyways, width like that. Hopefully that's fun. If I could get the right character. Okay, so width. Sorry about that. But regardless, what we're doing here is we're just setting up the display. So we're essentially saying this is how big the display is going to be. This is the dimensions. I'm making it width by width just so it's a square. And then I don't have to deal with any height variables later, which is going to make things a little bit nicer. Next, what we're going to do is we're going to set a caption for the display. So not in capitals, we're going to say pygame.display.set_caption. And for the caption, what we're going to do is just put whatever we want, but I'm going to put a star like that. And I guess I don't need to say star, a star pathfinding algorithm. This mic is really in my face, kind of in the way of the keyboard. So that's why I'm getting all these typos, because I usually look down a little bit, just pre-warning there. Anyways, we have that now. So width win pygame.display.set_caption. And now if we actually go ahead and run the program, we should see that a window pops up and then it just immediately disappears. So that's how you can test to make sure that this is working. You're not going to see anything right now. It's just going to go away pretty much instantly. But if that's working, good. Okay, so next, we're just going to define a bunch of colors. Now, I'm actually just going to copy these in. You guys can pause the video if you want to copy them out, but all this code will be in the description if you want to copy and paste different aspects of it. But I want to have all these color codes here because we're going to need to be using them for actually making the path and making the different squares and changing the color of things and all that. So we have red. This is a red, green, blue color code. Green, blue, yellow, white, black, purple, orange, gray, turquoise. Feel free to change all of these colors to whatever you want, but just define them in all capital letters as constants and have them here so we can use them throughout the program. Now, the next thing that I'm going to do is I'm going to define a class called Spot. Now, remember, we're building a visualizing tool. So I actually have to build kind of the main visualization tool before I can implement the algorithm, because the algorithm is going to be dependent on what our tool looks like, right? So we need to figure out essentially, how are we going to keep track of all of these different nodes that are in our grid? Because remember, we're going to do this huge grid. This grid is actually going to be a 50 by 50 grid, and we can change the dimensions of that if we want. And in that grid, we're going to have a bunch of spots or a bunch of cubes or whatever you want to call them. I like to call them spots, but you can call them whatever you want. You can even call this a node. That might even make more sense, but I'm going to go with spot. And this spot is going to need to hold a bunch of different values. So it's going to need to keep track of where it is. So what row column position it is in the grid, because this will just be one of those little cubes. It's going to need to know what the width of itself is, so it knows how to draw itself, right? If it is drawing itself, although I don't think we actually we will need to draw these spots because they're going to be different colors. And then it's going to need to keep track of all of its neighbors. That's something that's important, and a few other things as well. So its color will be the main thing because it needs to know, okay, am I a red node? Am I a green node? Am I a barrier? Am I the start node? Am I the end node? Which will all be represented by different colors if you remember the example that I did, and so on. And in fact, let me just run the example so you can kind of see what I mean. So we have like all these different spots, right? So when I click on one of them, it changes colors, and that's what the job of this spot class is going to be, is to keep track of the color of all of these spots and know what location it's in, right? So then when I press space, you can see there's red and there's green. And then of course there's purple as well that represents the path. So hopefully that makes sense. I just wanted to show you that's what it is. Okay, so class spot. So we're going to define an init in here. So we're going to say define init. We're going to say self. We're going to say row call width, which is just going to be, how wide is this spot, and then rows. Now I'm just going to call this total underscore rows. Now the reason I'm doing that is because we need to keep track of how many total rows there are here. You'll see why in just a second, but this spot does need to know that. And I want to avoid any global variables, so I'm just going to throw it right into the instance. So I'm going to say self.row equals row. I'm going to say self.call equals call. I'm going to say self.x equals row times self.width. Or actually, this is just going to be width. I'm going to say self.y equals call times width as well. Now the reason I'm doing this is because I need to keep track of the x, y, like the actual coordinate position on my screen, because when I draw things in Pygame, I can't just say, okay, draw it at 5, 5. I need to draw the actual cube, which is going to have some kind of width. It's going to be sitting in some position, so I need to know what position that is, and I can determine that because let's say I have 50 total cubes and the size of my screen is 800. Well, then I go 800 divided by 50, which I think is like 16 or something like that. And that will be the width of each of my cubes. So I can figure out where the starting X and Y position is by taking the row that I'm at and multiplying that by the width of all of these cubes. That's the idea there. We're going to say next self.color equals white. So to start, we're going to have all white cubes. This will again change as we go through. I'm going to say self.neighbors, oops, if I could type here, equals a blank list. And then I'm going to say self.width equals width, and self.total underscore rows equals total underscore rows. Next, what I'm going to do is I'm going to make a get underscore pause method, and we're actually going to have a bunch of methods in this class, and this is just simply going to return self.x, or not self.x, self.call, and self.row. And sorry, it's going to be the other way around actually, self.row, then self.call. So for this specific program, I'm going to be indexing things using row columns. So that's just what we're doing for the grid, right? If you look at the grid, of course, we have a bunch of rows like that, and we have a bunch of columns down. So, something like here could be indexed with, I don't know, like 6.3 or 6.4 or whatever it may be. But we start by calling the row out, so whatever y coordinate, and then I call the x. May seem counterintuitive or counterproductive, but the way we're going to represent the data, this makes sense later. Okay, so we have get pause. So now we're going to define is underscore closed. So is closed essentially like, have we already looked at you? Have we already considered you? Those are the red squares. So in this case, we're going to say, okay, what makes a spot closed? What would mean that this spot is in the closed set? So we're not looking at it anymore. What makes it red? Well, I pretty much told you that. We're just going to return self.color equals red. So the idea behind all of these methods here is we're just going to have a bunch of methods that essentially tell us the state of this spot. And we're going to have a bunch of methods that allow us to update the state of this spot as well. So they're just going to be changing the color. And if this color is white, well, then this is a square that we've not yet looked at. We could visit it. If it's red, we've already looked at it. If it's black, it's a barrier. That's something we have to avoid, that the algorithm can't use as a node to visit. If it's orange, it's the start node. If it's purple, it's the path, right? If you get the point. So this might not be the best way to do it, but this is what I've gone with for this tutorial. And I think it makes it pretty easy to understand. So we'll say is open. So is open is just going to be return self.color equals green. So essentially, are you in the open set? Now, I don't know if we are even going to use that method, but I'm just defining all of the different states just so it's consistent. So next we're going to say is barrier. So are you an obstacle? Well, what makes this an obstacle? That's if the color is equal to black, right? So if it's black, because we're going to punch it in and we're going to draw all the obstacles, then this is a barrier. So that's what we're doing. Next, we're going to say is underscore start. I'm going to say self, and we're going to say return self.color equals, and for the start color, we'll just go with orange, but you're welcome to change any of these colors, of course, if you'd like. And then finally, we go is end. Actually, there should be one more, and we'll return self.color equals, and I think I went with purple for the color. Finally, I'm going to add another method, and this one's going to be called reset, and this is simply going to change the color back to white. So define reset, and we'll just say self.color equals white, like that. Okay, now you thought I was done with all the methods, but we actually have more. This is like the longest class that's just the most simple thing in the world. But I'm going to say make underscore color, and what am I saying? Make color. I'm going to say make open, make closed, and pretty much duplicate all of these methods here with just a make in front of them. So when you call this, it will make this cube whatever it is that I'm saying here. So in this case, we'll start with closed just so it stays consistent. So make closed self, and I believe make closed was, what color were we going with? I think that was red, right? So we're going to say self.color equals red. So this time, instead of just giving them back, like, are you red? Are you green? Are you blue? This is going to actually change the color. So make closed, we'll say make open. This is going to be self, and we'll say self.color, equals green, like that. We have more. Oh, that's nice that that went away. So to make open, what else do we have? Make barrier, make underscore barrier. This is going to be self. And then we'll go self.color equals black. Okay. And define make underscore end. This is going to be self, self.color equals, and what was the end color? That was, I'm going to go with turquoise actually for the end color. And instead of purple, I'm going to change this to turquoise. My bad on the end color, guys. I want that one to be turquoise. And then we'll say define make underscore path self.color equals purple. So purple will be the path, turquoise will be the end color. And then finally, we need to add two more methods. So define draw. So this is going to be the method we call when we actually want to draw this cube on the screen. So we're going to say self win. So this is actually going to be this window. So essentially, where do we want to draw this? That's what this argument is saying right here. So self win, and I think that's all I need. And then to draw a cube in Pygame, you go pygame.draw.rectangle, so RECT, like that. You put the window, you put the color, so that's self.color, like that. And then you put a rectangle that you want to draw. So you give it an X, Y, width, and height. And you can see it's saying surface, color, rect, width. That's just telling us, how do you want to draw this rectangle? Where do we want to put it? What position? That's how Pygame works. So the way Pygame works, actually, let me just run this example here, is you start drawing things from the top left-hand side of the screen. So 0, 0 is actually where I just put this start dot. So technically I shouldn't be able to do that, but that's fine if that happens. See where this orange cube is, or let's put it there. Where the orange cube is, this is actually the 0, 0. So this is 0, 0, not down here, like where you would normally think. And as you move to the right, X increases. As you move down, Y increases. So over here in the very corner where the turquoise dot is, that would be 800, 800 if this was 800 by 800, which it is. So that's the idea with the XY. When I start drawing something, I always start drawing from the top left-hand corner. So if I say like I'm drawing at 50, 50 and the width is 16, then you're actually going to extend to like 66, 66. So you go from 50 to 66, 50 to 66 if you're talking about the lines. Hopefully that makes sense, but I'm just trying to kind of illustrate to you how that works. Okay, so we're going to go pygame.draw.rect. We're going to say self, and in this case, not row and call, but self.x, because that's the actual coordinate position I want to draw at, and then self.width and not height, width again. So since we're not doing a height, everything's square, we can just pass in width twice, and that'll just make it a rectangle. And then finally, we're going to say define update underscore neighbors. If I could spell neighbors correctly, like that. This is going to take self, and this is going to take a grid, and we'll do this one later because this one is kind of a big function. And then lastly, I'm just going to say define underscore underscore LT underscore underscore, just so I don't forget to do this. We'll talk about what this does in a second. Other, and we're just going to return false. Now, for any of you that don't know what this LT is, it stands for less than, and essentially this is how we handle what happens if we compare two spots together. So now what I'm saying is essentially if we compared this spot and some other spot, so two spot objects, I'm just always going to say that the other spot is greater than this spot. Yes, I think that's actually, maybe it's the other way around, but regardless, don't worry about this right now. We'll talk about it when we use it, but I just don't want to forget, so I'm putting it there right now. Okay, so the next thing I'm going to do, just because this one's really easy, is I'm going to define the heuristic function that we're going to use for our algorithm, right? So we need that h function. We actually need to make that heuristic function. So let's code that out. We're going to say define. I'm just going to call this h actually. And I'm just going to put p1, p2 here, and p1 and p2 are going to be 0.1, 0.2. So I'm expecting 0.1 and 0.2 to look like xy, right? Or to be like row column or something like that. So we have to figure out the distance between 0.1 and 0.2 and return that. So the way we do this, because we're going to use Manhattan distance, which essentially is L distance. So I'll show you how that works on the grid right here, is we just do a very basic formula. But essentially L distance, or like Manhattan distance, is say I have like these two cubes. The distance I'm going to calculate between them is going to look like this. It's just going to be whatever the quickest L is to get here. This is going to be my guessing distance because we can't move on diagonals, right? And even if you could, so if we can move on diagonals like that, that's still going to be the same distance as just going in an L like that. So that's what Manhattan distance is. It's sometimes called taxi cab distance as well, because it's like if you're going in a straight line and you're moving around and all that. But hopefully that makes sense. That's the distance we're calculating. So to do that, I'm just going to say x1, y1 equals p1. I'm going to say x2, y2 equals p2. This is because this is going to be a component, right? So if I have like p2 is going to be made up of something like, 1, 9. So I can split it into the variable x1, y1, where x1 would be 1, y1 would be 9. By just doing that, it's a shortcut in Python. And I'm going to return the absolute distance, ABS, this is a built-in function, of x1 minus x2 plus the absolute distance of y1 minus y2. Doesn't matter if you swap x2 and x1, so long as you swap y2 and y1 as well. Okay, so that's the h function, that's our heuristic. Now what I need to do is I need to actually come up with a way to make a grid. So I need some data structure that can hold all of these spots so that I can actually manipulate them, I can use them, I can traverse the grid, right? I need this list that's going to hold all of the spots that I have in my grid. So what I'm going to do is I'm going to say define make underscore grid like that. And inside of here, I'm just going to take the rows and the width. So I'm essentially saying, okay, how many rows do you want in your grid? Because we're just going to have the same amount of rows as we do have columns. And what do you want the width of this grid to be? So that's what we're doing. So I'm going to say grid equals a blank list. And I'm going to say gap equals width integer division by rows. So width will, of course, be the width of our entire grid, and rows will be how many rows we have. Doing an integer division will just give us what the gap should be between each of these rows, or in other words, what the width of each of these cubes should be. So hopefully that makes sense. And now we're just going to go ahead and actually create this. So I'm going to say for I in range, and I guess it's just going to be rows. We're going to say for j in range rows. Up here, we're going to say grid dot append an empty list. We're going to make a 2D list that looks something like this, with a bunch of different rows in their own list that all have spot objects inside of them. So we say grid, we have the gap, and we have grid dot append for j in row range. Now we're going to say spot equals a new spot. So we're going to use this class that we just defined up here. We need to pass it its row, its column, its width, and the total amount of rows in the grid. And then there, it'll be able to figure out where it should actually be sitting. So we're going to say ij for row column, because this is going to be our row. This is going to be our column. So we pass it ij. We're going to pass it the gap. That's going to be its width. And we're going to pass it rows. So now we have this spot object that we've created. And what we need to do is we need to append it into the grid. So we can say grid.append spot like that. And that should actually be, grid, I believe it's grid I.append spot. So what this is going to do is say, okay, in grid row I, which is the row we just created here, we're going to append the spot into it. So we have a bunch of lists inside of lists that all store spots. Then at the very end of this, we're going to return, if I could hit the T key, we're going to return grid. Awesome. So now we have the actual grid being able to be created, and I'm just going function through function because I think it's easy to just code out these small parts that all do separate things and then kind of combine them together at the end. So we have make grid, and now we need a way to draw the grid. So we have all these cubes, but remember, all these cubes are just like white cubes or black cubes. We don't actually have any grid lines. So if you look at this, right, you can see these gray grid lines, and like all my cubes, you can really clearly see kind of where they are and, you know, where they're defined. So we need a way to draw these grid lines that we have. That's what I'm going to do here. So I'm going to say define draw underscore grid like that. We're going to take inside of here the win, the rows, and the width. So this is not actually going to draw every one of the cubes that are inside of the grid. It's just going to draw those grid lines. So this is pretty easy to do, actually. I'm going to say gap equals width integer division rows. Again, that's going to be the exact same thing as up here. I could have made this all capitals. In fact, to stay consistent, let's make this lowercase like that. And we're going to say for I in range rows like that. And then here we're going to draw lines. So for every row, we're going to draw a, I believe, horizontal line first. So pygame.draw.line in this case. And what we're going to draw is a horizontal line for each one of these rows. So to do that, we need to pass the win, we need to pass the color, which is gray, and then we need to pass two positions, so two XY positions where we want the start of the line to be, where we want the end of the line to be. So the start of the line, we want to be at X position 0, and we want the Y position to be I multiplied by gap, like that. And then for here, we want this one to be width, and then I multiplied by gap. The reason we want that is because we're going to multiply whatever the current index of the row that we're on by the gap. And what that will do is it will essentially tell us where we should be drawing the grid line. So if we start at 0 width, we know we're going to be all the way on the two borders of the screen, and then we're just going to move those down constantly and draw a bunch of horizontal lines. Now we'll do the exact same thing. I'm literally going to copy this for loop, and I'm just going to change the variable to be j. So for j in range, so now we're going to do the vertical lines. And what we can do is just leave j times gap, but leave that as the x, and then as the y, we're going to go 0 and width. Like that. So tab that in. I'll explain this quickly. Essentially, this is the exact same thing as the horizontal lines, except I'm flipping the coordinates. So now we're always going to be at the top and bottom, and we're going to shift along the x-axis and draw all of those vertical lines. So I think, let me just make sure. Yeah, that's it for doing that. And next, we're going to actually make the main draw function, which is going to draw everything. So we're going to say define draw, and inside of draw, we're going to take win grid. So we need an actual grid that's being passed here. We need the amount of rows, and we need the width of the screen. So we have win grid rows width, and then in here we're going to say win.fill. So this just fills the entire screen with one color. You do this at the beginning of every frame. So we're going to run 100 frames per second or 50 frames per second or whatever it is. And at the beginning of every frame, we're going to paint over everything that was on the canvas, and we're going to redraw everything in its current state. It's not the most efficient way to go about doing things when you talk about drawing things on the screen, but for our purposes, totally fine. And this is common practice in Pygame. So we're going to fill everything with white. And then what we're going to do is we're going to say for, in lower cases, for row in grid. So for all those rows, and we're going to say for spot in the row, because remember, this grid is going to be whatever this creates. So it's going to be a 2D array or a 2D list. And we're going to say spot.draw, and we're going to pass the win. So essentially, if we go back to spot.draw, you can see this just draws its own color on its X, Y, and whatever the width it is. So it just draws a cube with whatever color this spot is, right? That's all it does. So now we just need to call that method on all our spots, which are going to be stored in our grid, which are stored in the rows. So we loop through all of it, go through all the rows, and then draw all of the spots. Next, we draw the grid. So we say we're going to draw the grid lines now on top of that, because this will be drawn first. So we fill the screen, we draw all the colors, we draw the grid lines on top, and then we'll be good and we've drawn everything we need to draw. So we do draw grid, we need to pass that win, rows, and width like that. And then finally, we do pygame.display.update. Now there's nothing that needs to go in here. All this tells us is, hey, Pygame, take whatever we've just drawn and update that on the display. Awesome. So next, what we need to do is we need to write a few more functions. So the next function I'm going to write is a function that can take a mouse position, and figure out what grid or what, I don't even know how to describe it, what cube or what spot we actually clicked on. So if you imagine, let me just boot this up here for 1 second. I have to be able to figure out which one of these spots to change colors when I click the mouse, right? Now, this is pretty easy math, but essentially I have to figure out based on where my mouse position is in this screen, because right here it's at 0, 0. In the bottom right-hand corner, it's at, 800, 800. I got to figure out based on whatever position it is, what cube I'm clicking inside of. That's what this function is going to do. Given a mouse position, it's going to translate that into a row column position representing the cube that I actually clicked on, so I can do things like draw a maze and all that fun stuff. So let's figure out how we do that. So we're going to say define get underscore clicked underscore position. So this is just telling me, where did we click? So get clicked position. We're going to take a mouse, if I could get inside of here. We're going to take a pause, which will be the mouse position, and we're going to take the rows and the width. So first thing that we need to do is we need to define the gap. So we're going to say the gap is equal to the width over the rows, so integer division. And then we're going to say I, j equals position. So essentially we're going to say, okay, like the x, y, we could actually do this. Maybe this will be easier. Let's go, the yx is going to be equal to position. And we can say row is equal to I over gap, and call is equal to, not I, sorry, this is y, to x over gap. So the reason this works is we're figuring out, we're pretty much just taking whatever the position is in the x and whatever the position is in the y and dividing it by the width of each of the cubes. So that'll give us where we are and what cube we've clicked on. I can't really explain that much more. And then we'll just return row call like that. So we'll be getting the row column that whatever person clicked on, and this is just a helper function that is, nice and easy to use. And now we're off to the main function where we're actually going to start setting up some of these events and start drawing some things on the screen and seeing how all of this works. So we're going to say define main. This is going to take a window and a width like that. This is going to be our main loop. This is kind of usually you start with this, but I just wanted to get all kind of the easy stuff out of the way, all these, basic functions and this class and the more tedious stuff before we did this, so we didn't have to keep going back and changing. This is our main loop, and this is going to determine essentially all of the, checks that we're doing. So all of the collision checks, all of the, when you press space, start the algorithm. When you press on this cube, change the barrier. That's what we're doing inside of here. So maybe a little bit more complicated, but shouldn't be crazy. So I'm going to start by defining the amount of rows we want to use. So I want 50 rows. The way I'm going to do this, you can quite easily change this number to whatever you want, and it'll just make a grid that has more cubes. In fact, I have my other example up. Let me show you what I mean. Now, I have 100 cubes, and we can quite easily run the algorithm on this. It's just going to take a little bit longer because there's a lot more cubes. So I'm setting it up in a dynamic fashion such that, everything is completely changeable. And that's why this might take a little bit longer, but it's nice because you can make it as big or as small as you want. So we're going to say rows equals 50. We're going to say grid equals make grid. If we go like that. What we need to pass to make grid is the rows and the width. So we have rows like that, and we have the width. So now make grid, which we just defined up here, is going to actually generate the grid and give us that 2D array of spots, or a 2D list, whatever you want to call it. Next, I'm going to define the start position and the end position, which to start are going to be none. We need to decide those. And then I'm going to say run equals true and started equals false. So essentially just some variables to keep track of the start and end position, if we're running the main loop or not, and if we've actually started the algorithm or not. So now we're going to say while run. So while this run variable is true, we're going to say for event in pygame.event.get, like that. And what this essentially is saying, okay, at the beginning of each of this while loop, let's loop through all the events that have happened and let's check what they are. So an event could be someone pressed down on the mouse, so they pressed a keyboard button, or a timer went off. Whatever events happen in Pygame, we're looping through them, and now I'm going to check them. So I'm going to say if event dot type equals pygame dot quit in all capitals. This is always the first one you should check. And what I'm going to do is I'm going to say run equals false, like that. And what this is essentially saying is, okay, if we press that X button at the top right-hand corner of the screen, then stop running the game. And at the very bottom of this while loop, I'm going to say pygame.quit. Oops, so pygame.quit. And what this does is it just exits the pygame window. So and whenever we hit this line, which will only happen when the while loop stops running, do we quit. Now, the next thing I'm going to say is if started, continue. Now, the reason I'm putting this here is because once we start the algorithm, I don't want the user to be able to press anything other than the quit button. So this while loop will be running when the algorithm is running, right? But if the algorithm has started, they shouldn't be able to like press anything. They shouldn't be able to change the obstacles. Like that'll mess stuff up if they do that. So that's why we're saying if started, continue. Now, the next thing to check, and this is really some of the only commands we need to do here, is if the user pressed down on the mouse. So if the user pressed on the mouse, we need to potentially draw a barrier. We need to do the start position. We need to do the end position. There's a bunch of different things we need to check, right? Because if you see the way that this works, it's a little bit small now, I apologize. When I press the first and second time, that does the start and end position, and then I can do the barriers, right? And if I right click somewhere, I can remove the start position and I can put it back to wherever I want. And if I right click on any of this stuff, it deletes it. So we need to check that. And there's a few checks to do here to make sure that like after I right click the start or the end position, I can place it kind of wherever I want, right? So that is what I'm talking about. And now you can see that the reason I did if started is so I can't just draw a bunch of barriers. Like I'm pressing down here and I can't delete the color on these squares. It just happens, right? And actually we'll let this run just because I find it so fascinating to see this thing just go and figure itself out. Like look at that. But hopefully that illustrates to you what we're doing here. So now we need to check the mouse position. So we're going to say if pygame.mouse.get underscore position, then what we're going to do, sorry, not get position, get pressed, get position will be next, and then 0. And what this stands for is what mouse button we pressed. So essentially we're saying if the Pygame mouse was pressed and we pressed on the left mouse button, so like your common mouse button, your clicking mouse button, then do something. Otherwise, so we're going to say elif pygame.mouse.get underscore pressed 1, sorry, not 1, 2, which is actually the right mouse button, I believe, then we're going to do something else. So if they press the left mouse button, do something. Otherwise, if they press the right mouse button, do something. And if you wanted the middle mouse button, you would do it with 1, right? So 0, 1, 2, left, center, right, if you're thinking about that. So that's what this says. This is, we'll do a comment, left, and this is right. Okay, so now inside of here, if they do that, we're going to say position equals pygame.mouse.get underscore position, so POS like that with a set of brackets. This simply gives us the position of the Pygame mouse on the screen, so what XY coordinate it's at. Now we're going to say row column equals, and guess what? We're going to use this helper function that we used that we just made. So we're going to say get underscore clicked position. We're going to pass the position, and then what else do we need? We need the rows, and we needed the width, like that. So there we go. So now this is going to give us the row and column that we clicked on. So this is what actual spot in our 2D list did we click on. So now we can actually access that. So we can say spot equals, in this case, grid, and oops, I just butchered that. We go grid and we go row col. So we can index the row column in the grid, and now, you know, we can do whatever we want with it. So the first thing we're going to say is, okay, if we have not yet placed the start position, we're going to need to do that, right? So we always do start and end position first. If the start and end position aren't down, when you click, you're setting the start or the end position. That's just the basic rule. If start and end are not there, if we haven't pressed them, then make them whenever we press next. So we're going to say start equals spots. That's why I have this start variable up here. And then we're going to say start dot make underscore. Do I not have a make underscore start? I thought I did. Okay, well, let's go back up to our thing here and let's make start, because I don't think I added that. Yeah, I just completely forgot that. So define make underscore start. I'm gonna go self. I'm gonna go self dot color equals, and I think we were going with orange for start. Yeah, I think so. So sorry guys, add that method make start, and then we should be good to do this. So now we're gonna say start equals make start, and then we'll say an elif, and we'll say elif not end, and we'll do the exact same thing for end. We'll say end equals spot end dot make underscore end. So hopefully this makes sense. We're saying if we press the left mouse button and the start or end one is not yet pressed, then let's make that the start or make that the end. And we'll always start by doing the start. After the start, we do the end. Now, otherwise, so in another situation where the start was actually defined, we've already done it. The end, we've already defined, we've already clicked it. If we're clicking and we're not clicking on the start or we're not clicking on the end, so elif spot does not equal end and spot does not equal start, then whatever spot we clicked on is just some random spot. We need to make it a barrier. So we'll say spot dot make underscore barrier like that. And that's as easy as this left mouse button press is. So now let me run this for you. So I'm going to call this function down here and let me show you what we've actually done so far. So let's run this. I'm like confident that I'm probably going to get an error, and my thing is lagging. So I'll be right back. Okay, so I had a small error here. I don't know, something crashed, something happened, but I also just realized that we just got to fill in a pass here just so I can actually test this right now, because I don't have an indented block for this other mouse position. And we're probably going to run into a few errors that we have to fix just because I've been coding for a while. So we'll go through these together. So main is missing two required positional arguments, win and width. So here, let's pass it to it, win, which I think was in all capitals, and then width as well. Okay, so win and width. I don't remember if I made it in all capitals. Yes, I did. So win width. We're just going to pass that to our main function, and hopefully now this will work. Okay, so we're getting a black screen, and the reason we're getting a black screen is, guess what? Because we never called the draw function. We never actually called draw, which will then draw the grid and draw everything else that we need to do. So what we're going to do is right at the top of our while loop, we're going to call draw. We're going to give it that win. We're going to give it the grid. We're going to give it the rows, which is all capitals, and we're going to give it the width. So now we'll call draw every loop, and this will just keep drawing everything. So let's try this. And there we go. We get a nice solid grid. And look, I can even go ahead and I can make all this stuff. So of course I can't delete anything now because we don't have the right mouse button set, but you can see that I can press and I can do it again. And let's run this one more time. And I can make my start and end position, and all is well and all is good. So I think that's about it. Now, what I'm just going to do here is I'm just going to fix this, because let's look at this for 1 second. If I press, so that's my start position, right? I can press my end position right on top of that. That's no good. That means the start and the end are the same, and we can't let that happen. So we need to handle that case. So now, before we actually assign the start, we need to make sure that spot does not equal end. And before we do the end, we need to make sure that end does not, or I guess spot does not equal start, so that we can't override each other. So let's just try it now. You can see that's the change in code right there. And now, see, it won't actually let me press it on top of each other. I was trying to, and you just can't actually press the spot on top of each other, which is exactly what we wanted. And now we can draw our barriers and obstacles and all that fun stuff. So now let's do the left mouse button, which is a little bit easier. So we're going to say position equals, and we're actually just going to copy these first 3 rows. Kind of counterintuitive to do it, but that's fine. We'll just copy all of them. We don't really need to worry about that too much. And we're just going to say spot.reset now. So essentially we have position, row call, and spot, which I've already discussed. And if you press on this spot with your right mouse button, I'm assuming that you just want to reset it to be white. So we'll say spot.reset, and we'll say if spot equals start, then start equals end, and if spot equals end equals none. And I mean, we can make this an elif, it doesn't really matter. It's going to be the same thing anyways, just to make sure that we reset, oh, not start equals end, start equals none, sorry. So we reset the start and end if you press on those ones, because those are the 2 variables that we're storing. So now let's run this and see what we get. So I can, right press and I can left press. Hey, my left click is not working for some reason. So I'm going to have to see, whoa, and there's a bunch of stuff going wrong. Okay, give me a sec, guys. I'm going to have a look here. Looks like something's happening with this update where something's kind of working, but it's not really working properly. So I'm just gonna have a look at this bug and see what's going wrong. So it looks like inside of my reset, we had 2 equal sign instead of 1. So that would make sense why it wasn't actually updating the color properly. So that would be the mistake there. So let's rerun this, because before it just wasn't actually erasing anything. And now when I right click, beautiful, it actually is working properly. So it looks like we've got kind of the main obstacle stuff almost out of the way here. And now the next thing to do is really actually just start writing the algorithm, which of course is the toughest part. But the visualization tool itself is kind of ready to go and everything's set up and handled. So the last thing we're going to do here is we're just going to add a event, and we're going to say if pygame.event.type, actually, sorry, not pygame, just if event.type equals pygame.key down. And now what we're just going to say is if event, so this is essentially telling us, did we press a key on the keyboard down? If event.key equals pygame.k underscore space and started equals false, sorry, not started equals false, and not started, then what we're going to do is we're actually going to go ahead and we're going to start running the algorithm. So the first thing we need to do in here is we need to now go back to the spot class and we need to update all of the neighbors of the spot class. So remember that what I was saying before when we were talking about how this algorithm works, we need to actually have neighbors for all of these spots. So these spots, we need to set this up as a graph. So every single node, which are all of these grid squares, need to have a neighbor beside them. So they need to have something to the left, something to the right, up, down, and that needs to be handled. So what we need to do is make this update neighbors method inside of spot, which will add into this list here, the neighbors list, all of the valid squares that could be its neighbor. So let's run this and I just want to show you, something's crashing. Let me just add a pass inside of here for right now. And let me show you what I mean. So like this orange square, for example, has this neighbor, this neighbor, this neighbor, this neighbor. Let me just move that over there. These 4 neighbors are this orange square's neighbors, right? But right now they're actually not, because these are barriers. So we can't use a barrier as an edge, which technically means right now there's no way for this orange square to connect with this green square because it's completely covered. It has no neighbors. So the point is that every single one of these white squares, we need to determine all of its actual neighbors that aren't these barriers, right? So we can't add these barriers as its neighbors because really, like say I do this, these circles here, all the white squares inside of these circles are now useless. We can no longer use them, and we need to make sure that we know the neighbors of like this white square and that we don't add this black square in there so that we don't traverse through any of the barriers, right? That's kind of what we have to do right now. It's not super difficult to do, but I just want to illustrate to you what this is. So let's go into the update neighbors and let's write this code. So essentially what we're going to do is just check up, down, left, right, and see if those are barriers or not. And if they're not barriers, we'll add them into the neighbors list. So let me just go have my reference code here to make sure I don't mess this up because this is a fair amount of code. We're just going to start by saying self.neighbors equals a blank list. And we're going to say if self.row, because we do have this, it's one of the attributes, is less than self.total rows minus 1 and not grid self.row minus 1 self.call.is underscore barrier, then what we'll do is we'll say self.neighbors.append, and we will append this. So we'll append grid self.row minus 1 and self.call. Now I know this seems like, what the heck did you just do, Tim? But this is, I'm checking if the row that we're at is less than the total rows minus 1. The reason I'm checking that, and sorry, this should be a +1, not -1, is because I want to add 1 to the row I'm on right now to go down a row. So this is going down, right? We're moving down a row because we start 0, 1, 2, 3, 4, so on like that. So we're moving down. So I need to check if I can move down, because if I'm on like square 49 or I'm on square 50 and I try to go to square 51 and that doesn't exist, I'm going to crash my program. So that's the check right here. And we say and not grid self.row +1 self.call.is barrier, then self.neighbors.append, blah, 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 append the next row down. That's what I'm doing. I'm saying we'll use the same column, but we'll add 1 to the row if we can add that to the neighbor. Now let's copy this exact same thing. and we'll actually copy it 4 times. We'll just update what these values are. Oops, let's just copy that if statement. Okay, so now we're gonna go down. Up is gonna be the next one. It's good to comment these just so sometimes you can read them pretty quickly. So down, up, left, right. So for up, we're just gonna change all the signs. So this is gonna be negative now. That's gonna be, oops, this isn't gonna be self.total rows. This is actually gonna be 0, and we're gonna say if self.row is greater than 0 and not self.row plus 1, self.call is barrier, then we'll say self.neighbors.append grid self.row plus 1 and self.call. Now I realize I messed something up here. This is a plus 1 and this is a minus 1. Sorry guys. So let me just space these out so we can actually read this. Okay, space like that. So this one, sorry. If self.row is greater than 0, so if we're not at row 0, and grid self.row minus 1, because we're going up now, not down, I was mixing that up, and this isn't a barrier, then what we'll do is say self.neighbors.append the grid of self.row minus 1, so the one above us at the same column. Awesome, that's all we need. Now, instead of call, we're going to say instead of row, we're going to say if self.call is less than self.total rows minus 1, then if not, self.row, so grid self.row, self.column plus 1 is barrier, then what we add is instead of row plus 1, we're going to do column plus 1. So now we're moving to the left. This is actually going to be to the right, and this one's going to be to the left. I'm just butchering these so badly. This is why I want to leave it to the end. But this is going to the right. So if we go to the right, we're just checking one square to the right. So we need to make sure that that's valid. If it is, append it into the neighbors. Hopefully I'm making enough sense to you guys. And then here, we're going to do the same thing as row. So if self.column is greater than 0 and self.grid and not grid self.row, leave like that, self.call minus 1, right? Then minus 1 will go there. Actually, it will go right there. Okay, so let me just make this clear. Make sure I didn't mess anything up. I think this is good. Essentially, you just have to make sure if you're greater than 0. If you're greater than 0, then you can subtract 1 without going into the negative numbers, so that's fine. And then if that one that we're checking is not a barrier, we can add that to the neighbors list. So we don't need to return anything from this. That's fine. That's enough for updating the neighbors. Again, I just butchered that so horribly, but hopefully that is enough. That makes sense. We're just adding the neighbors to all of those things. And here again is the code if you need to copy it down and pause the video or anything like that. Okay, so now that we have that, let me just go down here and we're going to call that for all of our spots. So we're essentially going to say for row in grid, and then for grid in row, or not grid in row, for spot in row, spot dot update neighbors. So this, whenever we actually press that space key down, so this is saying, if we press the key down, if the key is the space bar and we've not yet started the algorithm, then for row and grid, for all the spots in that row, update all of their neighbors. So call that method that we just created. After we do that, what we need to do is just call the algorithm. So we're just going to say algorithm like that. I'm going to pass in the arguments that we have already just because we're going to be using them inside of there. And then we should be good to go. So I'm going to say lambda, which I'll explain in a second because this is a confusing thing. I'm going to say draw, and I'm literally just going to actually copy this right here. I'm going to say draw like that. I'll again explain why I'm passing this in a second. I'm going to pass the grid, I'm going to pass the start position and the end position. So I've not yet made this function. We're going to code that out in a second. But what I'm saying is that, okay, once we start, we're going to call this algorithm function. We're going to pass a function that is equal to a function call. So I'll explain lambda, and then grid, start, and end. So what lambda is an anonymous function. So if I go lambda x like that, or if I said like x equals lambda, and then I say print inside here, and I go like print hello, calling x will call this print function. The way this works essentially is like, you can imagine that I'm just saying like function, like if I go like def func, and then it's like that. So I say like x is equal to defined function print hello. If I call x, which is just another name for this function, then that's calling hello. It's hard to describe this, but it's just known as an anonymous function because you don't need to give it a name. You can just kind of put it on a line. And this is great because this means I can pass this draw function as an actual argument to another function. And then inside of there, I can just call this directly. So again, it might be a little bit confusing, but just imagine that I'm just calling this draw function whenever I call whatever is represented by this lambda. Okay, mouthful. Let's now go and code out the algorithm, and then we're going to be pretty close to done. So underneath H, I'm going to define algorithm. I'm going to say draw, and then I forget what else I had here. I'm going to have to go look at this to make sure we don't butcher this. So this is draw, grid, start, and end. Awesome. So essentially what I'm saying is I'm taking a argument here, which is draw. This is a function that I'm going to call. So I'm going to call draw like that. And the reason I can do that is because lambda was like, lambda, let's just say print hello. If I say like draw equals lambda print hello, this is a function that calls that function. So if I call this draw function, it will do whatever is here, which is print hello. So in this case, draw is a function. So I can just call the function and it will do whatever draw is. Hopefully that's kind of making sense. But anyways, that's the best I can do. Okay. So next, what I'm going to do is I'm just going to define some variables. And this is where we're actually going to start coding the algorithm. And there's going to be a lot of explanation. So I'm going to say count equals 0, open set equals priority queue, which we'll talk about in a second. Remember, we imported that way at the beginning, at the very top of our program from queue import priority queue. Let's move this down, by the way. So say open set equals priority queue. We're going to say open underscore set dot put. Now this is put instead of push or append. It's just what the API is for priority queue. And this just means add to the priority queue. Remember what the first step of our algorithm was? It's to add the start node with its original F score, which is going to be just 0, right? So we add the start node with its F score into the open set. That's the first step. So that's what I'm doing right now. I'm going to say, okay, open set.put, and we're going to put the F score, which is 0. We're going to put count, which is 0. And the reason I'm putting count is just to keep track of when we inserted these items into the queue. That is so we can break ties if we have, and if I spell count correctly here, so we can break ties if we have two values that have the same, what do you want to call it? Or not values. If we have two things inside of the queue that have the same F score, we can just go based on which was inserted first on which one to consider. So we have a tiebreaker essentially. So 0, count, and then start. That's what I'm putting here. Okay, so this is the actual node itself, or the spot. This is some number. It's going to be 0 to start, and that's the F score, which is 0. So open set.put. We're going to say came from, which is pretty much keeping track of where we came from, right? So what node did this node come from? Remember, like I had, node B came from node C came from node D, and that's how we keep track of the path. That's what this dictionary is going to do, and that'll be more clear as we go. Next, we're going to have our G score. So we're going to make a table here that's going to store all of the G scores. So I'm going to say spot float inf. So essentially, we're going to have a key for every spot inside of our G score. It's going to start at float infinity, right? So this just gives us infinity. That's how you do infinity in Python. We're going to say for row in grid for spot, in row. So this is just a list comprehension. This is the same as writing like for row in grid for spot in row, G score spot equals float inf if we just do like a long drawn out way. But since we're going to do this twice, I'm just doing it in a list comprehension or a dictionary comprehension. And then we're going to originally set the G score of our start node, right? So G score of start is going to be equal to 0. Because, of course, the G score of the start node is just 0. Now we're going to copy this exact same thing, and we're just going to replace G with F because we need the same setup for F. And same F score is going to be 0 for our start node. And actually, sorry, the F score of our start node will actually just be the heuristics. So it's not actually going to be 0. I misexplained this. It's going to be the distance, which is going to be the heuristic from H of our start dot get position. So get underscore pause, and our end dot get underscore pause. So sorry, this was a mistake on my part. The G score and the F score are, or the G score is set to 0. The F score will just be the heuristic because we want to estimate approximately how far away this end node is from the start node and just give that H score already. So that'll be the F score for our end node. The reason we do this is to make sure that we don't, when we reach the end node, we don't automatically assume that it's the best path. I hope that kind of makes sense, but just imagine that like we start the F score of our start node at infinity. So sorry, I misexplained this, but essentially the reason the F score is just equal to the heuristic is because we do actually want to make an estimate of how far away this start node is from the end node when we begin. It's not a huge deal. It's not going to be super important, but the reason we have that is to make sure that if we say circle all the way around back to the start node, we don't take that as the shortest path because it was infinity beforehand. We just take whatever we think is going to be the shortest distance, which is just the heuristic. Again, it's not a huge deal if you understand that or don't understand that, but just make this equal to our heuristic, which is this H function right here. We should be good to go. Next, I'm going to make open underscore set underscore hash equal to a set of start. Now, the reason I'm making a set here is because this priority queue doesn't actually have anything to tell us if a node is in the queue or not. And we need to check in some sense if there's something in the queue or not. So if we have a value in the queue or if we've removed a value from the queue or whatever it is. So we need to have open set hash that is just going to keep track of all the items that are in the priority queue and all the items that aren't in the priority queue. So I can remove an item from the priority queue, but I can't check if something is in the priority queue. Where here, I can check if anything is in it because this will just be a hash that just stores all the same things that this priority queue stores, but just doesn't have the same kind of data structure implementation to give us the smallest item, if that makes any sense. Again, this is getting a little bit into some complex data structure stuff, but don't worry about it too much. Hopefully this will make sense as we continue. So we're going to say while not open underscore set dot empty. So essentially the algorithm runs until the open set is empty or not. So if the open set is empty, then that means that we've considered every single possible node that we're going to. And if we've not found the path yet, a path doesn't exist. That's what that says. And we're going to say just here quickly for event in pygame.event.get. Now, since we have a while loop, I need to make a way that people can exit this while loop. So if I say I need to just have this event thing here to let them hit that X button if they want to quit. So I'll say if event.type equals pygame.quit in all capitals, then what we'll say is pygame.quit. So this again is like we already have this down in the lower section, but since this algorithm here takes over and has its own loop inside, I need a way to exit this loop just in case something goes wrong. We can quit, or if it's taking too long or whatever it may be, we need a way to quit. Now, after we do that, we're going to say current equals open set dot, and I believe I can just say get, and I'm going to index at 2. Now, the reason I'm indexing at 2 is because our open set is going to store the F score, the count, and the node. Now, I want just the node. So I'm going to start at the very beginning of all of these loops by popping the lowest value F score from my open set. Now, if there's two things that have the same F score, we'll look at the count, and whatever was inserted first will be what I take. So that's what current is saying. This is the current node we're looking at. So remember, same example here. If we're starting at the very beginning, current will start as the start node because that is the only thing that's in the open set to start. So then what we're going to say is open underscore set underscore hash dot remove, I think it's remove, yeah, dot remove current. So we're going to take whatever node that we just popped out of the priority queue, and we're going to synchronize it with the open set hash by just removing it from that to make sure that we don't have any duplicates or anything out of sync and messing us up. Next, we're going to say if the current is equal to the end, so if this node that we just pulled out is the end node, we found the shortest path. So we need to reconstruct the path and we need to draw that path. So for now, I'm just going to say pass, and we'll deal with this after, but this is going to be make path like that. And we're just going to return the value true and just say, okay, we found a path. We're going to exit out of there. So I actually don't need the pass, but we are going to have to continue this after, and we'll do that later. Okay, so if current equals end, boom, that's it. And now next, what we need to do is we need to consider all of the neighbors of the current node. So we're going to say for neighbor in this case, we're going to say current dot neighbors like that. So if the neighbor is in our current dot neighbors, right? So for all of them, we're going to say the temp underscore g underscore score is going to be equal to the G-score of whatever the current score is plus 1. Now, the reason for this is because we can assume that all of the edges are 1, right? So if we want to figure out what the temporary G-score of this neighbor would be, assuming we go to this neighbor from whatever current node we're at, then we take whatever the distance is to this current node, the currently known shortest distance, and we add 1 to it. Because we're going one more node over, which is a neighbor of this node, we know it only takes one value, so that's totally fine and valid to do. So we add 1 to whatever the current score is for the shortest path to this current node. Then what we say is we say if temp underscore G-score is less than the G-score of the neighbor. So essentially, in other words, if we found a better way to reach this neighbor than what we had found before, update this way, update this path, store it, and make sure we keep track of that. That's what we're doing, right? We're trying to determine the best path to get to every single node. And from there, we can really easily kind of target ourselves towards the end node and find the optimal path. And that's what we're doing. So we're saying if the G-score that we're getting by using this neighbor is less than the G-score of what we had on the other neighbor, so the actual value, then go ahead and change things around. Update the value, say this is a better path. So we're going to say first came from, so the came from for the neighbor needs to be updated to equal whatever node we're on right now. So came from neighbor equals current because it's a neighbor of the current. We came from that. We're going to say G-score of current is going to be equal to the temp G-score that we just have right there. And then we're going to say the F-score like that. Oops. The F-score is going to be equal to, so the F-score of current, sorry, what am I saying current? This should be neighbor. My bad, guys. Sorry, this is neighbor. I don't know why I was typing current. So the G-score of neighbor equals the temp G-score. Of course, that makes sense. The F-score of neighbor equals the temp G-score plus the H of, in this case, it's going to be the neighbor, like that, dot get underscore position, because remember, we need the row column position, not just the spot itself. And not neighbors, it's going to be neighbor. And then this is going to be end dot get underscore position. So let me just assure that I typed that correctly. Yes, I think I did. Essentially, get pause, remember, is that method we wrote all at the beginning right here that gives us the row and gives us the column. So we need to pass that in because the method that does the H, if you look right here, expects 2 positions, not 2 spot objects. So that's how that works. So we update the F-score, and now we say if the neighbor is not in the open set hash. So this is why we're using the open set hash so that we can check if the neighbor is in the open set or not. So if it's not in, increment the count because now we're adding something in. So if it's not in, we add it into the set. So count plus equals 1. And we're going to say open set dot push. Or is it push or is it put? Sorry, it's put. And now we're going to put in this new neighbor, right? Because we're now going to consider this neighbor because it has a better path than what we found before. So we're going to put in the F-score. So we're going to say F-score of neighbor needs to go in here. We're going to put in whatever the count is. We just added 1 to it. And then we're going to put in the actual spot object itself, which is going to be the neighbor. So that goes into the open set. And then the open set hash gets the same thing. So open set hash dot add neighbor. Just because we're just going to store the spot in there. We don't care about the F-score and the count. And then we're going to say neighbor dot make underscore closed. So this is essentially saying, okay, we're going to make this current neighbor that we just put here closed so that we know we've already considered this neighbor. And that's making me look for, or sorry, not closed. This is going to be open, my bad, because we just put this into the open set. Of course, it's not closed. It's going to be open. It's green. We put it in the open set. And then finally, after this, what we're going to do is we're going to tab out. So outside of the for loop, we're going to call draw. And we're going to say if current does not equal start, then we're going to say current dot make underscore closed, like that. So what this is going to do is essentially say, I mean, I just went fast through it, but we've pretty much finished this entire algorithm, so I can show you how it works in a second. If current is not the start node, make it closed. So that's saying that if the node that we just considered and we just looked at is not the start node, we just make it red and just close it off because we've already considered it and it's not going to be added back into the open set. If it is, it will be made open and we'll see that, right? So that's the idea behind this. Now, of course, we need to reconstruct the path. There's a few small things we need to add, But this is pretty much it. And at the very end here, I'm just going to return none or return false to say, hey, we did not find a path. So that is this entire algorithm. So let me go through a quick summary, and then we'll actually run this and make sure it works. So we have a count, we have an open set. We start by putting the start node in the open set. We have came from. This keeps track of where we came from, so what nodes came from where, so we can find the best path at the end. G-score keeps track of, again, the current shortest distance to get from the start node to this node. We initialize them all at infinity to start, and then we set the G-score of start to be 0. F-score, this keeps track of our predicted distance from this node to the, to the end node. So going through this path, so following this path with this node, how long do we think it's going to take, or what do we think the distance is going to be to get to the end node? And then we set the initial, so these are start at infinity, just like G-score. And F-score, we start the initial F-score of start to just be the heuristic, so whatever our guess is from the start node to the end node, which makes sense because right now it's going to cost us 0 to get from start to start, so the only distance we need to go is whatever our heuristic distance is, right? And then open set hash, this is just going to help us see if something's in the open set, and then we have our while loop that says, okay, while the open set's empty, make sure that we're not quitting the game. If we are, let's quit, get out of this. Current equals openset.get2. So what that does essentially, and in fact, I could actually just return from this if I wanted to. Let's leave it pygame quit. So current equals openset.get2. The open set is a priority queue. The priority queue is just an efficient way to get the smallest element every time out of it. It uses a heap sort algorithm, I believe, to do that actually. And you don't have to know what that is, but essentially it's just a very efficient way to get the minimum element from this queue. So it gives us the minimum element, whatever the minimum F-score is. We get the actual node associated with that, or the spot object. We remove that from current, or from the open set hash, remove current from the open set hash. We say if we're at the end, we found the path, we finished, boom, we're done. Otherwise, consider all the neighbors of the current node, calculate their tentative G-score, their temp G-score. If that's less than whatever their G-score is in the table, then update that because we found a better path, and then add them into the open set hash if they're not already in there. And that is the very, very basics of how this works. So now what I'm going to do is go ahead and run this and show you the visualization. So I won't be surprised if we made a few minor mistakes and we need to rerun some stuff, but let's just go ahead and do this and press space. And what is the problem we're getting here? So let's see what's happening. Update neighbors missing one required positional argument grid. Aha, okay, so that makes perfect sense. We need to go down here to where we're calling update neighbors and just pass grid into there, and hopefully we should be good now. So self.spot.update neighbors grid, let's run this and see what we get. Okay, and there we go. This is actually working and we have the visualization going. Now, of course, we don't have the path being reconstructed yet. That's the last thing to do, but we can see it hit that end node and boom, perfect. It found it, right? And it went. And we can see that it didn't consider every single node. It actually just went, pretty much right to the node and had a pretty efficient path to find that. So now let's reconstruct the path, which is actually going to be really easy to do, and then we will be done. So now inside of here, I'm going to say reconstruct underscore path. I'm going to pass came from, and I'm going to pass the current node, which is actually just going to be the end. So we can just pass end, and I'm going to pass draw. Now draw again is that same function they passed in. Let's make another function up here and let's say reconstruct underscore path. Let's take came from end and what was this, draw. Okay, now inside of here, all we're gonna do is we're gonna say while current is in came from, so while it's in that list, what we're going to do is not current. Let's rename this current. So instead of end, this is going to be called current. So while current is in came from, which is that table that stores, A came from B, B came from C, C came from D, so on and so forth. Then what we're going to do is we're going to say current equals came from of, what is this going to be? Current. And then we're going to say current dot make underscore path. And we are going to, at the end of here, draw. Okay, So I'll explain this really quickly, but this is pretty basic. We're saying, okay, the current node starts at the end node. We're going to traverse from the end node back to the start node. The start node is not in came from. It's not in there. So that's fine, right? We don't put anything in came from for the start node. So once we get to the start node, we're done. But essentially, current will be equal to whatever we came from the last node. So from the end node, what do we come from? Some node, that's current. Make that part of the path, draw it, and then keep doing that. And then once we get to the point where we're at the node that came from the start node and we hit the start node, it will stop and it will stop reconstructing the path. So that should be it. Let's run this. And I'm just going to actually say end dot make end here, just because if you don't do this, essentially what will happen is it's going to draw purple on top of the end node. And I'd rather just have us be able to see start end and then the path in between. So anyways, that'll make sense, but let's run this and see if this works now. So I'm just going to literally press space. You can see, boom, that's the path that we discovered. And there we go. Now, one more thing that we should do is, first of all, let's run this and see if we can get a more complex example that works a little bit better. I want to make a way to like reset this and clear the screen. And by the way, don't feel bad if yours is running a lot slower than this. I'm on a very fast computer right now. But let's go to a way to reset this so that we can just run this as many times as we want without having to close the program. So this is going to be pretty easy. I'm just going to make another command inside of here. So underneath this if statement, and say if event.type equals pygame dot, and it should actually just be indented one more. So not event.type, we'll say if event.key equals pygame.k underscore lowercase c, then we're going to clear. So what this will do is it just clear the entire screen, just make everything white. So then we'll be good to go and good to start again. So I'm just going to make sure I'm not messing this up, but I think we can just say start equals none, end equals none, and grid equals make grid. And we need to pass what for that? Rows and width. Okay, so that should be it for clearing. The way this works is we'll just reset start end node, just remake the entire grid, which means that everything will just get reset automatically. And then we should be good to go. And yeah, I think that should literally be all we need to do. Yeah, so I think that's good. I'm just gonna add one more thing to this case space thing. I don't think I need this started thing actually. I haven't even used it. So I'm going to say if event.key equals pygame.counterspace and start and end to make sure, hey, we have an end and a start node before we do this, because if we don't, that's going to crash. So of course we need that first. That's a necessary thing here I should have had before. If we have a start and end node, then we're good to go. And I can remove this if started thing because we're not even going to use that. So we can get rid of started. Okay, so now we should be good. Let's run this and let's see what happens if I press C. So C clears everything, resets it. Let's run this and let's press C. You can see it resets and then we can go as many times as we want. So this is the pathfinding algorithm. This video has taken a tremendous amount of time to make. This is not an easy thing, but a lot of you guys asked for it. I think it's really cool, and I wanted to make something that was just awesome that you guys could really appreciate, you can mess with. And I love these programs. They're so cool. They're really what got me into programming when I was a kid. So I hope you guys enjoyed. If you did, make sure you leave a like. Please subscribe to the channel, leave a comment, let me know what you thought of the video. And of course, I will see you guys in another YouTube video.